Geometry students. I'm going to try to get an exam review video in before it starts to rain, and so today we are focusing on all sorts of different types of graphs, and let's see what we can do. So in Algebra 2 we have learned a bunch of different types of equations and functions and graphs, and so that's probably one of the primary themes is what it has. Every time we've been asking about what domain and range are, because they're all a little bit different, but the theme throughout the year is that domain always means the x-coordinates that the graph exists for, and range always means the y-coordinates that you can get out of a graph. And so as you're doing this project, make sure you include domain and range both in general and with the specific example that you make. So for this, I put everything into Desmos, and so let me see if I can get myself back on the top here so we can always see me, because that would just be annoying to not see me. There we go. All right. So, hey Penny, did you get some mail?
Yeah.
Awesome. You want to bring that inside? Awesome. All right. So, first type of graph that, well, not the first we ever learned, but the first from this semester that we learned were radical equations. These are things like this. It's got square roots or cube roots. So, a square root graph is a unique graph because it has a definite starting point and it only exists in one direction. And so the coordinates of that starting point are crucial. And to find those, you think about what makes this radical 0. That would be a 4 in this case. And so that's the x-coordinate. And so the domain is definitely x is greater than 4. Notice how that part of the graph shows up now. The range is, again, related to that starting point. In this case, the y-coordinate of that would be 5. And the range then would be described as y is greater than 5. Technically, both of these should be or equal to's. But that's domain and range for a square root function. Another type of function that's kind of the same shape and yet vastly different is a cubed root. So a cubed root graph definitely has this kind of here, and it takes off in one direction, but it also goes in the other direction. And this most important point is called an inflection point. You can find its coordinates kind of the same way by thinking about what makes this 0 and so forth. But in this case, the domain would be all real numbers because the graph goes in both directions. And the range is also all real numbers because it goes up and down forever. So there's square root and cube root graphs. Another type of graph that we learned was an exponential graph. And so here is an example of an exponential graph. Exponential graphs definitely are kind of like, well, let's go from this direction, kind of like airplanes. They go straight and then they take off. Or they could come down for a landing and they flatten out. But they have what's called an asymptote. And so an asymptote is a line that this graph seems to exist, come towards. Yes, Penny? What's that? Screen time probably is going to be an after lunch thing. Sorry, bud. Kids these days. Anyway, the important features is, yes, where that asymptote is, because that affects the domain and the range. Well, the range. The domain for this is all real numbers. So you can see horizontally, it certainly goes off in all directions that way. It's not so obvious that this graph continues that direction as forever, but it does. So the x-coordinate, the domain is all real numbers. The range, however, is definitely only above wherever this asymptote is, which in this case is this +5 that's there. So the range would be y has to be greater than 5. And in this case, it is not or equal to, because you never actually reach a height of 5. You're always slightly above it if you go in this direction. Desmos is not doing a very good job because it's so close to 5 that it had to round to 5, but it really is something like 5.0000001 or something like that. So a couple other important features that this graph has I want to try to call your attention to. So the 4 that's in front here, that is a starting height. And this starting height in this case has been shifted over a few spots because of the x minus 3 that's there. And another important feature of these graphs is that every time you take a step in the x direction, this height above the asymptote in this case it doubles, but it multiplies by whatever the base is. And so here this height is 4 steps up from the asymptote, here it's 8 steps, here it's 16 steps, and so on. So that's some of the important features that an exponential graph has. While kind of on this same screen, I wanted to show a log graph, because a log graph kind of has that same feature. If you tilt your screen, I guess that doesn't work for you guys, but it's got an asymptote as well and curves off in one direction, only this time it's flipped. And so it's got a vertical asymptote. And that vertical asymptote, where it happens, is pretty important. It's going to be determined by what makes this argument inside 0. And so in this case, 4 would be it. And it affects the domain and range. In this case, the domain it affects because x can only be greater than 4 then. Oops. So notice how that's the only spot where this graph exists. The range is all real numbers because this part of the graph goes down forever, and this part rises to reach any height eventually, although you might have to zoom quite a ways out to see it reach a height of 10 or 20 or 30 or something like that. See ya, Penny. So that's a log graph. Yes, ma'am.
There's mail from you and Mom.
There's mail from me and Mom?
Mm-hmm.
Great. Do you want to say hi to the people on the video that you're interrupting?
Hi.
Wave. All right. I got to get back to my video. See ya. Love you. Okay. I think I was basically done with logarithms. So let's move on to a new type of graph. So next thing we learned, this was in chapter 9, were about rational equations. And so rational equations are various sorts of curves. They can come in a lot of different flavors depending on how complicated the top and the bottom are. But some important features they usually have horizontal asymptotes, and they usually have a vertical asymptote too. The important thing to find a vertical asymptote, you look at the denominator and see, is there any way that could be a 0? In this case, if x is -2, that would be a 0, and that is why this graph has a vertical asymptote at -2. Technically, it doesn't exist. If you try to plug -2 in, you divide by 0 and you get an error. And so that's why this feature happens. In order to find any horizontal asymptotes, it's a little harder. There's no straightforward, obvious way to do it. What I suggest is plug in a big number, like 100 or 1,000, and see what this gives you. If you plug in 100, you're going to get a number really close to 3. Sometimes you can also find that by looking and finding a various feature in here. Another aspect is just graph it. Graph it and kind of zoom out and see what happens along the edges. And in this case, this graph kind of flattens out at 3. And so that's its horizontal asymptote. These affect the domain and range then. So the domain is generally all real numbers except for any x's that make the denominator 0. And so in this case, -2 would be out of the domain, and we say that the domain is all real numbers except -2, and we usually write that by saying x cannot equal 2. I don't think I can type that in Desmos. So, but that would be its domain. The range, again, is generally all real numbers, but in this case, I never actually reach a height of 3, and so you would say that the domain is y cannot equal 3. So that's rational equations. Moving on, we learned a whole bunch of different things about circles and hyperbolas and parabolas and ellipses in our conic sections video. I think the most important shape to remember in all that is an ellipse. It's probably the most normal occurring, and circles are special types of ellipses, so they fall into this category too. An ellipse formula is x minus something squared plus y minus something squared equals 1. And if you want to adjust how big or small it is, underneath the x term, you can put a horizontal radius squared, and underneath the y term, you can put a vertical radius squared. And so here is a picture of this particular ellipse, and the center you would see what makes this a 0 and what makes this a 0. So 4 makes that a 0, and 5 makes that a 0, and so 4, 5 is the center. The 8 that's underneath here is the horizontal radius. In fact, I think I can show those. Yeah, here we go. The 8 is this length here, and the 10 is the vertical radius. That's here. All the conic sections had focus points, and to find them with the ellipse, they're always going to be on the longer axis, which in this case is up and down. And the focal length formula, I usually have to look it up, I don't remember it, but in this case it's a squared minus b squared, or b squared minus a squared equals the focal length squared. And so in this case I had to do 10 squared minus 8 squared. That's the focal length squared. So that was 100 minus 64 is 36. Square root of 36 is 6. And so the focal length is 6. I think I can just show that line segment if I turn some of these things off. I think that was this one maybe. Nope. This one. So you can see this is the focal length was 6. And so you go up 6 from the center and down 6. And those are where your focus points are. Focus points have a lot of different applications, from audio to reflecting ideas to, well, yeah, I wish we had more time to be able to explore all the cool things that focus points can give us. But unfortunately, as you know, Algebra 2 is packed with a ton of things to learn. So the last the last type of graph that we learned were sine and cosine graphs. And so the basic sine graph, zoom in on that, is something that looks like this. It starts off in the middle, goes up high, comes back down to the middle, goes low, and ends back in the middle. And then this graph continues forever. So that basic pattern starts, and then it happens again and again and again. And so, though we didn't really talk about it a lot, its domain, the x-coordinates that a sine curve exists for, is all numbers. The range, however, is very much limited. The range, there's a highest point and a lowest point, and finding the maximum and minimum really depend on what is the multiplier in front of the sine and what is the part that's added to at the end. So the part that's added to at the end affects the middle of the graph. It shifts the entire graph up and down. We call that sometimes the midline. And so right now the midline is 2. And the number in front of it, that's often abbreviated with A because it's called the amplitude. That shows how far up or down above the midline we go. So yeah, that's that line segment that's drawn in blue. So here has a very small amplitude, and here is a negative amplitude. If you have a negative number, that inverts the graph. So instead of starting by going up, you start by going down. One other feature that these graphs have is because they repeat every once in a while, the amount of distance that it takes for a cycle to repeat is called its period. And normally, if there's nothing in front of the x, if it's just regular x, oh, my graphs get totally messed up. Anyway, if it's just x, then a graph usually goes 360 degrees to repeat its cycle, or 2 pi radians to repeat its cycle. If you adjust that by putting in something like this, then you can make that period bigger or smaller. And so another thing to consider when you're thinking about sine and cosine graphs is what the mode that your calculator is working in. Are you thinking about it in degrees or in radians? And so to switch on a calculator, you press the mode button and go to either degrees or radians. In Desmos, it naturally thinks in radians, but you can change that to be degrees if you click the wrench and choose, I'm in the way. If you choose degrees instead of radians, it'll do that. So a good formula to remember or to memorize is this guy, y equals something sine of 2 pi over something x plus something. Or if you're in degrees, instead of 2 pi, that would be 360. That gives you control over the important features you need to typically control with this graph. Real quick, cosine curves and sine curves are kind of related, but a little different. The basic cosine graph, this is inverted. Let me switch back to regular. So the basic cosine graph starts high instead of in the middle and ends back up high again. And so if you have some scenario where it makes more sense to think about the highest point as a starting value instead of the average or the middle to start, then you might want to write an equation with cosine. But cosines, like sines, really do go on forever in both directions. We usually just think about one cycle at a time. So anyhow, I know that was a rush and kind of interrupted by some rain and some daughters, but I hope that helps a little bit. Please let me know if you're having trouble with coming up with an equation that might make sense or something like that. I will be glad to help you, and I'll catch you in the next video, hopefully later today, but certainly tomorrow.